So I got up here and drew chip in the box, right? Okay. So there's going to be more drawing on the board, which is hard for the people on the video to see because the camera's only taking pictures of the screen. But what we're going to do is cover counting in binary. And at a certain point, we're also going to do what's known as hexadecimal. And maybe you're already familiar with those terms, but I bet a fair percentage of y'all are not. So we're going to press boldly forth. Before I get on the board, I can probably just type a lot of it here. Then I'll get on the board and hopefully it'll make more sense. So, say we're in a car. We have an odometer in our car. It's only got 2 digits, right? Brand new car. We drive a mile. We drive a mile. We drive a mile. Okay, this is boring. We drive a mile. We drive a mile. We drive a couple more. And we know instinctively, from training since kindergarten or whatever, what's going to happen next. So what mile are we going to get to? 10. Right. And why did we get to 10? Because we maxed out this column. We kept incrementing this column until we maxed it out. It reset back to its lowest value, and the next column was incremented. And of course, if we got all the way to 99, whoopsie, if we got all the way to 99, the same thing would happen, right? This column is maxed out, so what do they call it? Add and carry the 1 or something like that. That would reset back to the minimum. This one would be incremented. Incremented just means add 1 to it. Nope, oops, it's maxed out as well, so that one would be reset back to its minimum. And then if we had room for a third one, right, we get 199. If we didn't have room for a third one, it would roll back over to 0, 0. And I don't know if any of y'all have driven a car long enough ago that you've ever had it, nowadays they have like 7 or 8 digits, right? You could drive a car for 1 million miles before it rolls over. But, it used to be that they didn't expect cars to last more than 99,000 miles or something like that. So it'd click over at 100,000. So we know what's going on there instinctively. We need to talk a little bit more, though, about these place values. And yeah, that's a 1 place value, and that's a 10's place value and a 100's place value. Turn the light up just a little bit more. But what they really are is powers of 10. And you kind of know that too, but it's going to go somewhere. This is 10 to the power of 0, the 1's column. This is 10 to the power of 1, the 10's column. And by the way, any number to the power of 0, except maybe 0 to the power of 0, is always 1. For a reason that we could draw a mathematical proof for, but we're not going to. And so this is 10 to the 2nd power, right? Which is 100. That's about enough, right? I don't need to keep going. 1, 10, 100,000, whatever. This would be 10 to the 3rd, and so on. So we count by, incrementing the 10 to the 0 column. Once we max it out, this is the highest digit allowed in our system, resets back to 0, and we increment the next one. And we keep doing that, right, 20, 30, 40, 50, 60, 70, 80, 90, until we've maxed out both of these. They get reset to 0, and the next one is incremented. So that's our counting system. Did I have anything else to say about that? No. But imagine a counting system that didn't max out at 10. Since this is so-called decimal, des means 10, we have 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. No. Sorry. I was doing the Sesame Street thing of starting at 1 and going to 10. No. We go from 0 to 9. Those are our 10 digits. Again, I think I've said before, but computers, we always start counting with 0. And in our numeric scheme, we really start counting with 0, even though we go 1, 2, 3, 4, 5. But if somebody asked us to count, we really got to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because this one, is 2 digits, not just 1. Now we're going to make up a system that doesn't have 10 digits. Maybe it's got 8. That used to be common in computer science back in the 60s or something. It was called octal. Octal meaning base 8. So if we were going to write down the powers of octal, well, the numbers for octal are 0, 1, 2, 3, 4, 5, 6, and 7, right? That's 8. You ever wondered why October is the 10th month, not the 8th, and November, which means 9, is the 11th month, and December is the 12th month? It's because two Caesars, Julius Caesar and Augustus Caesar, just inserted their months in the middle of it, screwing this up. But anyways, so we have octal. It's not going to be 10 to the power of 0, and 10 to the power of 1, and 10 to the power of 2. Since this is octal, which means 8, it's going to be 8 to the power of 0, 8 to the power of 1, 8 to the power of 2. And I'm not going to go further than that. Anything to the power of 0 is always 1. That's the ones place. Anything to the power of 1 is itself, right? And then what's 8 squared?
64.
Yeah, so that's 64. So these are our places. Instead of 1, 10, and 100, we have 1, 8, and 64. So if we were going to count an octal, get my hands dirty, we would go, here's our odometer, 0, 1, 2, 3, 4, 5, all the way out to 9. No, we can't get to 9 because our system only has the digits 0 through 7. So when we get to 6, we've maxed it out. So it rolls back to 0. We add 1 to that column. That was 0, 0, 0, 1, 0, 2, all the way up to 0, 6. It's now 1, 0. Looks like 10, all right? I don't know what you call it when it's octal, right? But it's 1, 0. And then if you kept going, dot, 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 and they kept both rolling over, nope, 7, yeah. Why did I say we stopped at 6? I said the top one was 7. I know y'all get the right idea, but I just goofed, right? 0, 6, 0, 7, 7 is the max. That's where it rolls over. And say we kept rolling over and we kept rolling over and we hit 77. Well, the 7 is maxed out, so it goes back to 0. The 7 is maxed out, it goes back to 0. And so now it's 1, 1, 0, 0. Right, so we had zeros all the way down here, and then finally, we got a 1 there. That means 1 times 8 to the power of 2 plus 0 times 8 to the power of 1 plus 0 times 8 to the power of 0. Now I'm just going to make up a number. Say we're talking about decimal, which I'm going to represent by doing that after it, mean parentheses 10. Say we have the number 3, 2, 1 in decimal. What that really means, and this is a long way to go about it, 1 times 10 to the 0 plus 2 times 10 to the 1, don't go to Twitter yet, let's just keep struggling through it, plus 3 times 10 to the 2. So what is this? 1 times 10 to the 0 is 1. 2 times 10 to the 1, that's 20. 3 times 10 to the 2, that's 300. Once we added them all up, we would get 321. That's a long way to get from there to there. But it applies over here as well. So say we have the number 3, 2, 1 here. Actually, I'm going to make it 1, 2, 3 because once we start multiplying large numbers together, my brain breaks. So what is 3 times 8 to the 0?
3.
Yeah, that's the 1's place. That's the x place. That's the 64. So that's a 3 times 10 to the 0, which we're going to say is 3, plus 2 times, not 10 to the 0. What is it?
8.
8 to the 0, right, okay. Plus 2 times 8 to the 1,
16.
which is 16, right? Because 8 to the 1 is 8, so 2 times 8 is 16. Plus 1 times 8 squared, 64. And now if I add these correctly, right, isn't that something like 83? All right. So this number in octal, which I could represent like this, 1, 2, 3, parentheses 8. The parentheses 8 just means it's octal. It means 83 in our counting system. Now, why did the computer scientists in the 60s like octal? Because it was a power of 8. And you could represent octal numbers by even powers of zeros and ones. We will get back to that point. But I would just say that right now, that 3 bits, which are 3 zeros and ones, 3 zeros, for reasons we will talk about, is a 0. 3 ones adds up to 7. That's the same series of digits as that. Just keep that tucked in the back of your mind as we go to binary now. Can y'all see this when I write on the one with it? Should I turn the projector off? Is the glare bad? If it is, let me know. All right, binary. Base 2. It only has 2 digits, 0 and 1. That's what computers do. Absence of a charge, the presence of a charge, 0 and 1. So, the first rightmost column is 2 to the power of 0. And then we have 2 to the power of 1. And then we have 2 to the power of 2. So, 2 to the power of 0 is 1. 2 to the power of 1 is, and 2 squared is 4. So, if we have this number, 111, which is the highest we could count with 3 bits, right? Because we can't put 2s and 3s and 4s. It only has those digits. Well, that means 1 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. And so what's 1 times 2 to the 2? What's 1 times 2 squared? So that's a 4. What's 1 times 2 to the 1? Well, 2 to the 1 is just 2. And what's 1 times 2 to the 0? So when we add those up, we found out that 111 in base 2 adds up in our system to base 7. Hope that kind of makes sense.
So depending on the base, changes with zeros and ones are gonna be.
Yeah. Based on the base,
Okay.
they have different column positions. In our counting system, 10, base 10, it's 1, 10, 100, 1,000, 10,000. In this counting system, 1, 2, 4, guess what this one is? 8, 16, and 32, and so on. And for that powers of 8, it was being multiplied by 8 each time, right? Because when we were doing powers of 10, 10, 100, 1,000, 10,000, we were multiplying by 10 each time we moved up. For base 8, we would be multiplying by 8 each time we moved up. I'll never mention base 8 again. We're going to be talking about binary. And so the 1 and the 0 pretty much mean the same thing, regardless of whether you're talking about decimal, octal, binary, whatever, because that's the complete absence of anything, and this is 1 of anything. You couldn't have base 1, because base 1 means that there's only 1 digit in it, 0. Base 2 is the smallest you can get in a counting system, because base 2, you have 2 digits to play with, 0 and 1. Base 4, you would have 4 digits, 0, 1, 2, and 3. Base 2 is what's important to us, so we're going to work a little bit more on that. Is that kind of making sense, guys? Are we having more fun than we can handle, or just enough? I think it's just enough. All right, so what we're going to note here is that this is base 10 counting, which means 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so the first column well, if we're going to do it, it's 10 to the power of 2, 10 to the power of 1, and 10 to the power of 0. Those are our three placeholders, place values. So that's 100, that's 10, that's 1. So if we have 1, 2, and 3, convert 1, 2, 3 base 10 to base 10. That's stupid, right? We're converting it back to itself. This means 1 times 100, or 1 times 10 to the 2, plus 2 times 10, plus 3 times 1, which equals 1, 2, 3 base 10. All right, there we went in a circle. We got back to our place. And so when we're counting, just kind of finishing these notes out. I'm going to make a note here. We have maxed out the ones place. So we set the ones place to 0. And then increment to tens place. And so on. Then it keeps going. 11, 12, and so on. So binary is not base 10. Binary, base 2, meaning 2 digits in our counting system, 0 and 1. So we have 2 to the power of 2. Whoops, star, star. I know that when we've been typing in the past, to the power of was always the caret. That doesn't work in this language. I don't know why he didn't choose that, but he used star, star instead. 2 to the power of 1 and 2 to the power of 0. Those are our three place values, which if we multiply them out, that's 4, right? That's 2, and that's 1. So if we have this number, 1, 0, 1, what does that mean? That means 1 times 10 to the 2, or we could call it 4. 1 times 4, plus, how many times 2? This is the number that we're converting. Convert 101 in base 2 to base 10. So, we took care of that one, but what's in the 2's column? Don't make me go and highlight it, guys. What's after this one? Going to the left. I mean to the right. That one. Right, right. What you were telling me is what we would be multiplying by, but what is the original digit? It's 0 times 2. And then, how many times 1? We're not talking to me anymore. There we go. Yeah. Maybe some of y'all got tired of giving all the answers, but the others pick up the slack, please. 1 times 1. And then if you add those together, what does that equal to? Well, that's 4. And then this one is 1, so the total is going to be 5 in base 2. All right, we're going to get a little more crazy. We're going to go up to 4 binary digits, which is 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. And so if we start here, that's the 1's place, right? What is that? That's the 2's place. What's that one? 4's place. And what is this one?
16. Well, 8.
You'd think, but it's actually 8, right? 1, 2, 4, 8, 16, 32, 64. I'd rather remember it that way than trying to remember what 2 to the power of 5 is, right? I can't do that automatically, but if I keep doubling it, it comes out okay. So that's the 8's place, that's the 4's place, that's the 2's place, and that's the 1's place. So if I come up with this number, what is 1101 in base 2? Converting it to decimal. Alrighty, we can figure that out. I'm going to push that up here. So here's our digits. 1, 1, 0, and 1. So starting off, this is 1 times 8. Plus, what's the next one?
1 times 4.
1 times 4. We're going to make y'all do these in just a minute on your own, so I hope this is starting to make sense. Plus, what's next?
1 times 2.
It would be 1 times 2, but what is the digit
Oh,
really?
1 times 1.
It's 0 times 2.
Oh, yeah, I skipped that one.
Yeah, so we could just skip it. I'm going to go ahead and just write it down, but, you know, it doesn't count for nothing. And then, what's the last column?
That was 1.
That's 1 times 1. So if we do this multiplication out, 1 times 8 is 8. 1 times 4 is 4. That's a 0. And that's a 1. So that's 13. Equals 13 in base 10. All right, kind of the shortcut. If you had to figure this out and you didn't whip out a scientist calculator or whatever, that would do it for you. If I have this digit right there, and I want to convert it to base 10, I could just go, well, that's a 1 in the ones place. How many 2's do we have? Any 2's? No 2's. Somebody on this side answer. What digit have I highlighted? That's a 0, so there's no 2's, so I'm not going to put anything there. And then what's in the 4's place? A 1, so that's a 4. Plus, what's in the 8's place? 0. Not going to even put anything down. Plus 1 in the 16th's place. Then if I add those up, that's equal to 21, base 10. So, even shorter. If I had 110011, 1 plus 2, 3, no 4's, no 8's, plus 16, 4 plus 16, I ought to be writing this down as 20. And what's double then 16? 32. Did I goof that up? 1 plus 2 is 3. And then no 4's, and then no 8's plus 16, so that's 19.
19.
Plus a 32, which is 51. So, you see how I did that? I don't want you to do it that way, at least if I ask you on a worksheet to do it. But, you know, after a while, if you did this all the time, and I'm sure you're gonna, no, I'm kidding. But, you know, 1's, 2's, 4's, 8's, 16's, 32's. If you can add those up in your head, great. Past a certain point, past like 4 of these, I can't do it in my head. You know, maybe 5. You know, my brain doesn't hold the numbers more than that. You saw where I stumbled right there. Okay, guys, I want you to pop out Notepad or idle. If you're going to do it in idle, sure, why not? Let's do it in idle. File new, and start a multi-line comment. A multi-line comment is 3 double quotes or 3 single quotes. Convert these numbers from binary to decimal. But we're going to set it up. Try to make it easy. This is going to be the 8's place, the 4's place, the 2's place, and the 1's place. Right? Just type that over and over as you need it. So here's the first number I want you to convert. Here's the second number I want you to convert. 1001. I think I've done that one. 1101. Here's the third one. 8421 0100. And then lastly, we're just going to do ones across. 8421. Those are our placeholders. 1111. Now I'm going to do this one for grins, and then I want you to do the other 3. So, 8 times 0 is a 0. I'm going to type it out long form. I want you to type it out long form this time, and then after this, you can skip the zeros. Plus, how many 4's do we have? We got 0. I wish we had like 4 people saying it better than 1. Keep saying it when nobody else does, but come on, guys. So we have 1. No zeros. Excuse me, no 4s. What's our next place?
2,
The 2's place. And how many 2's do we have?
1.
Okay. And then lastly, the 1's place. And how many 1's do we have?
1.
Okay. And if we added those all together, you know, no 8's, no 4's, but we have a 2 and a 1, so that's equal to 3 in base 10. All right. Do the next 3, please. Give y'all a couple minutes. And then I'll go over it, but, you know, there's going to be a test question on your midterm about how to do this. It's not going to, you know, make or break your entire life, you know, your entire grade based on this, but it's going to be a couple points. Eyeball. Okay, 15. Got it. When you put the parentheses, it's actually base 2 there, and that's base 2 there, and that's base 2 there. So you're going to put your answer, but then followed by parentheses 2. So when you're putting your answers, just put the number, then a parentheses. I told you to, it's 10. Our answers are 10. Followed by 10. So whatever this adds up to, 7, 14, I don't care. 14, parentheses, 10. 7, parentheses, 10, whatever. Did that make sense? Since I told you the wrong thing. Got it now. Of course you did. I can't see it. That's bad. My guess is that this one's not quite right. 8 plus a 4 is 12, plus a 1 makes it 13. You just did it. Okay, guys, if you get this part right, and then it adds up to the wrong number, like it was supposed to add up to 13 and you wrote 12 or something, you know, I'm going to give you credit for it because you got this right and you just kind of brain glitched on, you know, adding 8 and 4 and 2 and 1. Because this is actually the important part. Understanding that is more important than being able to add 4 numbers in your head.
I have a question.
Yeah.
How did you get that 10 like after the parentheses?
Pardon me?
How did you get that 10 on the answer? Like,
That's not part of the answer. It means decimal. It means base 10. It's just a way of writing it. I could have done this. 3 in base 10. That'd be a way to put it. Or 3 in decimal. But that's a shortcut. That makes sense, y'all?
Yes.
All right. I'm getting lonely, so I'm going to do this one as well. This is 8 times 1 plus what's next?
4 times 1,
Plus 4 times 1 plus what's
2
next?
times 0,
Yep, 2 times 0, and lastly,
1 by
1
1.
times 1, and I think that adds up to 13. Base 10. How's about this one? I made, 0 to 8 times 0 plus what's next? 4 times 1, and then the rest, the other 2's are zeros, so 2 times 0, come on, type, plus 1 times 0. So it's just that, right? There's nothing else in it. Equals 4 base 10. And we did this one before, but if we do it short form, that's just an 8 plus a 4 plus a 2 plus a 1, right? Short form. Long form, it's 8 times 1 plus 4 times 1 plus 2 times 1 plus 1 is equal to 15 in base 10. That makes sense. Anybody furiously typing and need this more on the screen before I go on? Wave me down if you need a little more typing time. Nope. All right. Back to the PowerPoint. And if we're finished with the PowerPoint, we're going to go to Chapter 2. I kind of forgot if we have or not.
Are we going to put this one here?
You're going to upload it at the end of the class.
Should we go ahead and save it, or are we going to add more to it?
Nothing wrong with saving it now, right? And then adding more to it. So File, Save As. Are we on Lecture D? Go to your favorite place. Lecture D. To end all of this green stuff, put 3 more quotes at the end. That stops the multi-line comment. So I'm going to go down to the very bottom here, type in 3 quotes of the same kind, double quotes or apostrophes, and now I'm ready to go. Whatever. And while we're at it, why don't we put our name and stuff up here? Binary and Chapter 1, which Chapter 1 does not cover binary, so that's why we did. All right, scrolling on down. Well, we're only at page 6. Well, we're going to go through this pretty quick because I think we've already talked about this. Have I drawn the differences between compilers and interpreters? Compilers make executables.
Yeah.
Okay. Don't want to waste time on repeating something. 3 kinds of errors. Well, this kind of says, nah, this isn't a description of the 3 kinds of errors. But I'll mention them anyways. 3 kinds of errors. Book only says 2. Daggone book. There are syntax errors. Program won't compile and run. There are logic errors. That's the second one that the textbook talks about. Program runs but gives you the wrong output. Right? You tell it to calculate what 100 degrees in Fahrenheit is in Celsius, and it says it's a million. But that's not true. That's a logic error. You tell it to calculate your yearly taxes, and it always comes up with 0. Well, that's great. You don't owe any taxes, but that's an error. So, program runs, but produces the wrong output. The textbook we used before we switched to this one called those semantic errors. I like logic error better. That's a better term. And then the third kind are runtime errors. Now, I guess the book's going to argue that a runtime error is the same as a logic error, but it's really not. That's when the program runs but gets into a state from which it cannot recover, and so it crashes. Like you're writing to the disk, but somebody ejects the disk. It's going to give you an error. You're trying to access the internet, but your Wi-Fi is turned off. You can't get a hold of the internet, right? Your program could crash if you didn't write it. You divide by 0. Sounds silly, but dividing by 0 will cause a runtime error. And you could argue that that's a logic error. You shouldn't have divided by 0. Yeah. But trying to write to a disk that's been ejected, it might be pretty difficult to predict in advance that that disk is going to be ejected halfway through. Or you try to open a file name, but the file does not exist. What should you do? You should pop up a message that says file does not exist, and maybe let them try again with another file name, right? That'd be the best thing to do. That would be handling it. It would no longer be a runtime error at that point. A runtime error is one that crashes the program. Crash because program reaches a state from which it cannot recover. So examples. I'm not going to tab all the way over there. Disk full, bad file name, divide by 0, stuff like that. You try to access your H drive, but there is no H drive on your computer, that kind of stuff. I'm going to put stars next to the ones that the book has mentioned. Book mentions the first 2. And would argue that a runtime error is a logic error, which I don't agree. Your program can have perfect logic, but it can still get to a runtime error. So logic errors. It's supposed to control a thermostat, and it's supposed to turn the heater on when the temperature gets below 32 degrees. But instead you write it so it turns the heater on when it gets above 32 degrees. That's a logic error. Produce the wrong output. It's supposed to capitalize the first letter of every word, but it doesn't capitalize any of them, or it capitalizes every letter in every word. Logic errors. So if I ask you for 2 of the 3 types of errors, you ought to be able to crank out, right, 2 of those 3. If you go for the first 2 because that's what the book says, great. If I say at least 2 and you feel like popping out with a third one, I might give you an extra credit point if it's an exam, right? We've talked about variables enough. They're giving us a more technical definition here. I'm going to give y'all a more technical one still. Here's what they say. And you hate when I cut and paste because you're typing the notes. So a variable is a named location in memory whose value can vary, right? Remember when I wrote down these addresses for Chip to play with? Address 0, 1, 2, 3, 4, 5, 6. It'd be a real drag if your program could only access memory based on its number, right? You always used address 5, to hold your salary, and you always use address 10 to hold the tax rate, and you always use address 20. Well, that doesn't work anymore because our computers have, 10 to 20 to 30 programs running at the same time. Like if we pop open the task manager and click processes, all of those are running at the same time. You don't know in which order they are. You don't know which memory addresses they're filling. It's actually a flaw in the operating system if you can figure out what memory address it's in, because then you might be able to access it and change it and make that program do something different, right? So maybe I can make Notepad save to a different file name if I knew what specific address it had loaded its file name into. Now, operating systems are supposed to go hand over foot, go to great amount of trouble to not only hide these memory addresses from each other's applications, but to not to allow your program to access something outside of its own private memory. So if Notepad tries to access a memory, address that's actually not owned by Notepad, it's part of Python, it's supposed to stop the program. I'm absolutely sure you Windows users have seen the error. The program has performed an illegal operation, right? And then the program's dead, right? It's because that illegal operation is actually it trying to access memory that doesn't exist. A common bug is not that you're trying to be malicious, but that it calculates the address with which to write to, but it tries instead to write to 0. Just because your variable is not initialized, it defaulted to 0. Okay, so we don't want to write to specific address numbers. We want to name those numbers. And by the way, back in the 50s and stuff like that, when computers were simple and only ran one program at a time, it was totally fine to say I'm always going to write to address 10, this number and address 20 and stuff like that. They didn't have the inventions of variables yet. That was a big step forward to create symbolic languages where you use variable names. So here's my definition of them. Or here's what a variable has. Variable has 4 components. It's got a name, good thing. It's got a type. It's got an address that it points to, and that address contains a value. Now this one's pretty cryptic, the address that it points to. It's only a very, very few languages, C and C++, that you care about what address it's pointing to, and you can actually get the address out. If I wanted to know the memory address of the salary variable, I don't even think I can get Python to cough it up. To do that in those programming languages, you use something called pointers, and pointers point to direct, memory addresses. You get the memory address of the salary, and then you can access it by pointer. We don't care. So what I really want you to remember are these. And when we're talking about variables, we usually talk about the first 2. Salary. And what type of data does salary hold? It holds floating point data. Last name. That's its variable name. And then its type is string. And its value may be Jeff or something like that. So I'm going to kind of put this one into parentheses. Also address. Just to say, yeah, it's 1, but the variable has 4 components. Please memorize the first 3. If you're going to go on to a 4-year college and take comp sci courses, yeah, then bring up your memory and learn the 4th one. Please memorize the first 3. Now this is a restatement that mentions it mentions all 3 of them. It mentions everything except type, right? Named memory location, yeah. Whose value can vary, yeah, it holds a value. It's a memory location, so it's an address. They don't mention this, and that's like one of the most important things. Because if it's a string, you can't do math on it. If it's a number, you can't, tack it on to the end of a name. You have to modify it in order to get it to be part of the name. Or you have to turn that string into a number and hope that they didn't type in garbage, right? Something that's not a number. In some languages, you have to specify the type before you can use a variable. And once you do specify the type, that's all it can hold. So, in C or Java or C++ or C#, a whole bunch of languages, you would do this. Int x, x equals 3, right? This declares the variable, and this puts a value into it. We might give these special names. That's declaring the variable, and that's assigning the value. So that's declaring the type. Python, a little bit more loosey-goosey. Now, if we try to store something that's incompatible, like a name, x is equal to Fred, boom, error. Because it's not the correct type. Because the variable can only hold ints. So example, C++ or Java. Python, you don't have to declare the variable in advance. You just go x is equal to 3. This sets the type of the variable based on its value. All of a sudden, it thinks x is an int. And it is. It can do anything that you can do with an int, right? You can do all sorts of math on it, or use it as an index counter or something like that. And then if you feel like turning around and saying x is equal to Fred, hey, no problem. It changes the type of the variable based on its value. This is what's known as a strongly typed language. You declare a string, strings are all you can put into it. You declare an int, ints are all you can put into it. You can't store floats. Python is not a strongly typed language or a strictly typed language. It's a loosely typed language. You want to store numbers in it? Great. You want to store names in it? Cool. We have more time to play with. I should be responsible and keep going through the chapter, but I'm eager to show y'all something fun, which is called turtle graphics. What do we say, fun or responsible? I'm thinking fun. You're going to read the rest of the chapter, and you're going to read the PowerPoint, and you're going to take the quiz based on it. But I think I've talked about the most important parts of it. That may not strictly be true. Do read the chapter, do read the PowerPoint, do take the quiz. Here's about where we're going to pick back up. But what we're going to do now is turtle graphics. And by the way, I guess I typed all these notes in. No, that's still a notepad. So I'm going to flip back to idle. Turtle graphics, like tortoises. That's what we're going to do now. Oh, when we pick back up, we're going to start on page 19. That's actually a good point to put into our PowerPoint. All right, so go back to idle. Don't type this stuff into the shell. As always, I just recommend closing this as soon as you get a programming window open. I'm just saving these notes as a text file. So if I close it accidentally, it's ready to go. All right, back to idle. Okay. Underneath the green text, we want to get some black text going. Now, there's something called the Turtle graphics library, but it's not part of the idle language. The idle language consists of the whiles and the ifs and the variable name, types, doubles and floats and, all that kind of stuff. But you can add on to what it does. You can expand it by creating functions and classes and libraries, and that's what we're going to take advantage of. Now what the Turtle graphics do, let's see if I can find it real quick. Mechanical Turtle graphics. I hope it pops up. If it doesn't pop up in 2 seconds, well, that's cute, but no. All right, I'll just describe it. Maybe some of y'all bought the BB droid, from Star Wars movies recently, and you could control it with your iPad, or your iPhone, and it rolled around and stuff like that. Well, what if it had a pin, and you told it to go forward, and then you told it to turn left, right 90 degrees. You told it to turn right 90 degrees again, go forward, turn right 90 degrees again, go forward. Now it's back where it started, and it drew a square. And so in the early 70s, some instructor or some scientist or whatever wanted to teach some children programming, so they invented a turtle like that, right? And it had a cable to it or something like that. And the kids could write a program that would tell it to go left, right, specify the degrees, lift the pin. Maybe it had several pins built in so that, it could draw in different colors. That's what we're going to do. We're going to draw lines on the screen by giving a turtle commands. Now the shape of the cursor is just going to be a triangle, but if you want to with a function call, you'd actually make it a turtle. But anyways, here we go. To get it to work and get the case correct, which is all lowercase at this point, there's going to be one uppercase letter in the next line. That's why I'm mentioning it. We have to import the turtle library. And we'll be using more libraries than just the turtle library. Think of these as plugins or additional modules, right? You install a spell check module onto your, your word processing program, or a new game pack or something like that. Import turtle. Now we're going to make a turtle, and I need to give it a variable name, like the Ninja Turtles, Leonardo. We're going to call this one Leo. Leo is equal to Leo equals sign turtle, all lowercase, dot uppercase T. Turtle, and in parentheses and in parentheses. Now, very good. We're going to set the turtle speed at kind of a middling speed. So Leo.speed, go to 5. 1 is the slowest, 10 is the fastest, but then if you set it to 0, it takes the brakes off and goes even faster. So we'll play with that in a minute. All right. Let's draw a square. So we're going to go forward, and then we're going to turn left, and go forward and turn left and stuff like that. But let's just get it to draw one line first, and we'll feel like we've accomplished something. Leo.forward, which you can abbreviate FD for faster typing. Go 100 pixels on the screen, going forward. Just because if I type forward, somebody's going to leave an R off somewhere. So abbreviations are cool, but if you want to type the whole word, that's cool. So then run it. It's going to ask you to save it. If you haven't saved it yet, go put it in your favorite directory. And it drew a line. If it did not draw a line, then we have a problem and I need to come help you. All right. We want to draw a square or a triangle?
Triangle.
Yeah, let's do a triangle. So the way you calculate the angles that are involved, we know what a right angle is. It's 90 degrees. But really, since there are 360 degrees in a circle, that 90 degrees is calculated as 360 divided by 4, because the square has 4 sides. If we had something that had 6 sides, 360 divided by 6 would be 60 degrees. Did I get that right? Yeah, and then it would draw a hexagon. But we want a triangle, so 360 divided by 3 is 120. So I'm going to turn left 120 degrees. Leo dot left 120. Well, we can kind of see that it's ready to go left, right? But we haven't told it to go forward again. It's kind of, locked and loaded. It's ready to go. So let's make it go forward. I'm just going to copy these 2 lines, and I'm going to paste them 2 more times so that we have 3 lines. Copy that. And paste. I like Control V for pasting, but you can always use the edit menus as well. If you like typing them all in by hand, you can do that. Now it's going to draw a triangle. And it's going to wind up pointing in the same direction as it was originally, right? Because it turned 3 times. Once, twice, 3rd time. If we tried hard, we could turn this into like a tri-star or something like that. I'm not going to do the whole thing, but we could go forward 100, and then we could turn, Let's at least draw a diamond. So we're going to go forward 100 again, and we're going to turn 60, then we're going to turn 60 and be back where we were. But this time we're going to be turning right. So Leo dot forward 100. Let's maybe leave that part off. Nah, we'll leave it in. And then Leo dot right, which you could probably abbreviate RT. 120 degrees. Now if we make it 90, we can make it kind of look like a house with a square on the bottom. So we're going to make it a right angle. Leo forward 100, Leo dot right 90. Now since we have a square, we're going to need to do that 4 times. So I'm going to copy that, and then I'm going to paste it 3 more times. One, 2, 3. I'm going to test it out. Now I'm going to try to get it to draw a circle. And I'm going to see if I can get this right. I might draw the circle and it might be in the wrong place. In fact, let's add the circle command first. And then we'll try. I'm hoping that I can get the circle to be right in the middle of the square. But if it's not, at least we will have seen a circle be drawn. I'm going to make a comment that these 4 parts are the square. So I'm going to put a comment up here above it, square. And I really ought to go up and put a comment above the first forward to say it's a triangle. You feel like adding those? Cool. If you don't, nobody's going to come get you. It's possible that I tell you I'm going to grade you on programming style, which means that I want you to put the comments in it. If I do that, don't put a comment on every single line. That's way overkill. But break it up into sections. Getting input, calculating tax, displaying results, that kind of stuff. And a description up at the top of what it's doing. All right, let's draw a circle. Guess what the name of the command is? Leo.circle 100. We're going to find out if 100 is the radius or the diameter. If it's the diameter, it'll be the same size as a square. If it's a radius, it'll be twice as big. I don't remember, so we're going to find out. It's the radius. And it went to the left rather than going to the right. That's useful information, and I'm not going to take the time to figure out how to get it down here and make it draw there. We could go with 50 so that at least it's centered, but I'm not going to bother. But let's make it do kind of a clover shape of 3 circles or something like that. To get it to have 3 sides, again, 360 divided by 3 is 120. So I'm going to make it go, doesn't matter, Leo.left, 120, and then copy those lines and paste them 2 more times, because I want 3 circles there, kind of in a triangle shape. If I wanted 4 circles, north, south, east, west, I would do 90 degrees, and I would have 4 drawings rather than 3, 4 circle calls. All right. Now that we've seen the turtle do its business, go back up to that speed parentheses 5 and change it to speed parentheses 0, just to watch it go fast as possible. So I'm changing Leo.speed way up at the top to speed parentheses 0. And it ought to go lickety-split. There we go. I like that. If I was going to draw a complex shape, it's fun to watch it go a few times, but after that, you want to speed it up. One more thing I want to make it do is we're going to move the triangle code into a function so that we can draw a triangle with a single call. Or then we can draw as many triangles as we want. Our drawing's getting kind of messy here, but let's go with it. So this code up here, these 3 calls, these 3 with 120 up at the very top under the speed, we're going to define. I need to switch to calling them modules. The textbook calls them modules the whole way through. From now on, if I say function, think module. If I say module, think function. They're the same thing. So DEF stands for define triangle, parentheses, end parentheses, colon. Now when you type the colon and you hit enter, it's going to be indented. Leave it that, well, we're going to wind up tabbing everything over. Once you have a colon, everything after it has to be indented until we're at the end of the module. So, you want to highlight all 6 of those lines after the DEF triangle, parentheses, end parentheses, colon, and indent. Just hit the tab key, or if you really want, you can choose format indent. I like tab keys, right? All right, cool. It's supposed to draw a triangle. It's not going to draw a triangle now. Why? Because although we defined the module, we didn't call it. It's like creating a map to Walmart, but I don't give you the map and tell you to go to Walmart. So we need to call the triangle function. So triangle, parentheses, end parentheses. And then let's go forward a little bit and draw another triangle. Leo.fd, like just 20. And then copy and paste those a couple times. We're going to draw 3 triangles in a row. Then we're going to stop. All right, so you saw what it did. One call, a triangle, made it do 3 things. It went zip, zip, zip. And then it went forward a little bit. It was sitting here. Another call, a triangle. So it went zip, zip, zip. Then it went forward 20 more. And we call triangle again, so it did zip, zip, zip. And then after that, we drew our squares and our circles and stuff like that. So what we did is we created a module that we can invoke to draw a triangle with a single call. If you feel like it, define a module called square while I'm creating the Dropbox and wandering around and making sure that everybody's got it going on. If you don't feel like creating a module called square, that's fine. What would you do? You just tab all this stuff over, put a DEF square above it. Let me make the Dropbox for those of y'all who aren't feeling that adventurous, and we will be done. Oh, and by the way, yeah, before I go away, before I end it, you see here it says 1 quiz is not attempted. I like that in good English. 1 quizzes. All this is a link to over in the quizzes directory. It says MindTap Unit 1 quiz, and if you start it, here's what it says. If it says. All right. Go take the Unit 1 quiz in MindTap linked above. Then come back and click True and submit. The only reason this is here is so that you see a due date somewhere reminding you to go do it. You don't have to do it every time you retake it. Just do it once to get this, off your itemized list. That makes sense? I'm not going to go into MindTap and assign dates there, because then if I assign a date, you won't be able to edit it afterwards. You won't be able to take it again, and I want you to be able to take it again as many times as you want. So I'm not going to put a due date in MindTap. We're just going to kind of track the due dates in the quizzes section of D2L. You got that?